Oh, okay. Well, we were going to wait for a moment. All right, good morning and welcome to virtual product validation and process visualization for off-highway and commercial vehicles. I'm Carl Bangert. Over the next hour, we're going to be looking at ways to ensure reliability of designs and manufacture of critical systems, including hoses, flexibles, and critical power distribution systems for vehicles. Presenting today is from Sandalwood Engineering. We're going to have John Lukowitz and Mitch Carswell showing various aspects of solutions we're going to present. Myself, I'm Carl Banger, General Manager of Flex Structures North America. A little bit about our organization. Sandalwood Engineering and Ergonomics has been around over 30 years with locations in the US, Canada, and Mexico, providing a number of engineering services in the areas of systems engineering, systems integration, and ergonomics and injury prevention. We're partnered together with Flex Structures. I represent Flex Structures, a company that's been around 11 years, based in Germany, providing software solutions dedicated to simulating flexible components, as well as products around a suite called Industrial Path Solutions for product and systems validation. The message today really is we're looking at systems and vehicles and products being electrified, but also in the off-highway section still needing the power that comes from hydraulics. And as these systems grow and become more complex, the issues that are keeping our customers up in this area involve reliability, whether it's fraying due to the relative motion of the systems, hydraulic leaks, and as we get electrified, managing the complexity of electric power distribution systems. For that, over the past years, we've had clients that have really taken the leap from doing things in the physical prototyping space, moving towards the vertical area. Virtual systems. So taking test labs, test systems that were involved costly physical mock-ups and really cleaning out the prototype lab, because the system simulation that you can do in the virtual space can give you accurate results and confidence and reliability years before start of production. And that's where really so much of an industry is headed to, no less here on the off-highway and commercial vehicle segment. So what we're going to touch on really is how these products work together with your own design and CAD systems to take you from a design static, drawing, if you will, which may be in 3D, being able to add flexibility of the cables and hoses, being able to look at assembly considerations using Path Planner to make sure that these components work together, fit together, and move together, and taking into account human factors. As we mentioned, ergonomics and injury prevention is a key portion of that. Developing strategies so that these power distribution systems can be installed as well as maintained and serviced is critical to what is being done. And that can be done on the computer as well as leveraging virtual reality, so that you can do these virtual studies, virtual assemblies, again, long before you've actually got metal created or the hoses, cables, and components in place. So that's what our focus is. We're going to start on today is cable simulation. John will take you through that, and then we'll move to the assembly portion on the side with Mitch Carswell. Should note is that what we're going to show is physically realistic systems as well. So the components that have been brought in are subject due to forces, due to gravity, and these can be augmented by measuring these components as well. So that's a service that we provide also. So whether you're talking about wires that go down to millimeter in cross section to 10-inch diameter hydraulic hoses, pressurized up to 500 bar. These are the kind of measurements that we can do to provide data that is physically meaningful for your virtual validation. With that, I'll pass it on to John to describe the virtual product validation using IPS cable simulation.
Thanks, Carl. In the interest of bandwidth, I'm just going to turn off my video here, and I'll share my screen. And as Carl mentioned, we'll begin by going through a couple of different examples of designing and optimizing cables and hoses in the IPS tool. I'll then take us through an example of the rigid body path planner, which is a tool for planning collision-free installation paths. And then I'll pass it over to my colleague, Mitch Carswell, to talk us through IMA, which is our digital human model, as well as some of the VR capability. So to begin here, we've got ourselves an excavator. And this is really what we can achieve in the IPS tool, where we have all of our flexibles modeled in a physically correct way in the presence of gravity. And this allows us to really understand and optimize our designs. Understanding how our flexibles are moving, their clearances to any surrounding components, what their bending radii look like, and we can also investigate any forces that we may be interested in. So let me switch models here to another excavator that does not yet have the flexibles model. So to begin working in IPS, firstly, we need some CAD data. And the IPS tool is compatible with many different CAD formats. So we can just import in some geometry to begin. We're compatible with JT, STL, VRML, as well as CATIA formats. And I should mention here as well that some of our clients have established direct connections between their PLM systems and the IPS tool. So we've seen connections between PTC Windchill, as well as Siemens Teamcenter directly into IPS. So now that we have some geometry, we also need a motion that shows us how this particular product is going to behave physically. How is it going to be moving and operating? We can create these motions directly in the IPS tool, but oftentimes they've already been created in some kind of external CAD system. Obviously, we want to avoid double work as much as possible. So we can very simply import in these motions and then simply link the geometries that we've imported in to get this mechanism to play without having to recreate the motion in IPS. And that's exactly what we've done here. So to begin, we'll take a look at an example with this hydraulic line on the upper arm here. We can certainly create flexible components in IPS from scratch, and we'll see an example of that a little later on. But if we have some pre-existing geometry from the CAD system, we can also take that geometry, make it flexible, do our analysis and optimization, and then feed that information back into our CAD or PLM system. So we've got some geometry here of our hydraulic line, and I'm just going to use a tool called the cable finder to automatically find this cable. We can see that the IPS tool has identified this, this hose's center line, as well as its cross section. You can see all of these kind of previewed circles along the length. And now we just need to tell the software a bit about this specific flexible. So first of all, what does its cross section look like? Very important to note that we can handle all different kinds of flexible components in the IPS software. So we can simulate straight cables. So basically any kind of flexible that would be straight when it's unloaded. But we can also simulate preformed cables and hoses. So if we have something that's pre-bent into some configuration prior to installation, we can certainly handle those kinds of flexibles as well. And then lastly, we need to tell the software a bit about the specific material properties of this hose. So there are several ways we can do this. We can just use basic material properties, density, Young's modulus, and Poisson ratio. As Carl mentioned, we also offer testing services. So if we want to have a really robust understanding of the very precise material properties of a particular flexible, we can test some samples of those hoses, cables to get these effective parameters. And then the IPS tool also comes with a library of predefined hoses and cables that you're more than welcome to use. So in this case, I'll just use this hydraulic hose 32 millimeter, hit OK, and then create cable. And now I've created this hydraulic line in IPS. Now that we've created this, the tool is very fast and interactive. So if I were to, for instance, take the end of the hose and move it around, we can see how this hose is behaving in real time. Similarly, if I twist the ends, we can see that behavior once again based on its specific material properties and the presence of gravity. So if I want this hose to move along with the motion of my excavator, I've just got to make a couple of quick connections here. There we go. And if I zoom out, I can click play on my motion and we'll see this hydraulic line moving along with our excavator very realistically. So now we probably want to do some analysis and optimization of this hose to make sure that it's going to meet our design requirements. And first of all, it looks like it could potentially be coming close to this upper arm here. So we can create a number of different measures to take a look at its interactions with this upper arm. So firstly, I can create a distance measure, basically just measuring the minimal clearance between any components in the scene. So I'm just going to say I want to measure between my hose and this upper arm. Any of the measures we're tracking are going to pop up in the bottom right-hand corner of the screen here. And you can also see this minimal distance measure identified by this green line, where exactly it's occurring. Right now it's towards the end. It looks like there could be potential for a collision between this hose and the upper arm throughout the motion. So we can also create collision tests. And I just need to tell the software what I want it to check for a collision between. And in this case, it'd be this hydraulic line and my upper arm. We have a few different options for these collision tests, but I'll just tell it to highlight when there is a collision. So it'll highlight this hose red. But we also have options to show a little more detail, right? So we could look at intersecting lines or colliding triangles between these two geometries. And then lastly, in the IPS tool, we also support contact handling. So if there is contact between some kind of flexible and another flexible, a flexible and some kind of rigid component, or even two rigid components, the software will actually calculate how those things are going to interact. And rather than passing through the geometry, we would want this hose to actually glide along it as it would very realistically in the physical world. So I'm just going to tell the software to check for contact between this arm and my hydraulic line here. And now that I have these measures set up, I'm just going to open up a little bit of a different camera view so we can see a little more clearly exactly what's happening with this line. And if I play through my motion, once again, we're going to see all of our any of the measures we're tracking updating in real time in the bottom right corner of the screen. We saw there that there actually is a collision throughout this motion between the hose and this upper arm. So you'll see this hose highlighting red when that occurs. And once again, it's going to glide along that upper arm, behaving exactly as it would in the physical world. So obviously this is an issue. If we can, we always want to avoid contact between our flexibles and other components. So we could very quickly and easily experiment in the IPS tool with some different routings to see if we're able to eliminate this contact. For instance, I could try rotating this fitting to see what effect that might have on the behavior of my hose. So I'll just rotate it 60 degrees, and then I'll open up my camera view again here to see what effect that had on this clearance between our hose and the upper arm. Notice now that our distance measure is all the way at the end of this fitting here. It looks like it's staying above about 30 millimeters throughout the course of the motion. And our hose is no longer highlighting red. So we've successfully eliminated contact between this hose and the upper arm. We have a number of different other analysis tools also available to us. So firstly, we can create visualizations, essentially color maps on any of our flexibles. So we can look at things like stripes for take a look at torsion, any number of different forces, moments, stresses. But in this case, I'm going to take a look at my bending radius. And then I can customize this color map based on my specific design requirements. So let's say for this application, a really good bending radius is 200 millimeters, and our minimum requirement is 160 millimeters. If I play through the motion once again, we'll see this color map updating in real time. So we can see as we move through the motion. And then here, we're seeing the hose turn red, which is identifying that we're dropping below that minimum bending radius requirement of 160 millimeters. So beyond being able to just visualize these things, we can also directly measure them. So I can create a number of different value measures on any of my flexibles, looking at things like elongation, tension, strain, once again, any number of different forces, moments, stresses. But in this case, again, I'm going to create a value measure for my bending radius. And we'll see that pop up in the bottom right-hand corner of the screen as well. And now if I play through my motion, we'll see how that value is updating in real time. So we can see we're above 200. And then as we go through the motion, we're dropping below 160. So it looks like we're well below our minimum requirement here. So an fairly obvious solution to improve this bending radius would be to add some length to our hose. And we can very quickly change the length of any of our flexibles in the IPS tool by simply right-clicking. And we can use these arrows to very quickly add or remove length. Notice that bending radius updating in real time. Or we could type in some specific value to see what the effect might be. Beyond just sort of playing around with these lengths and routings, we also have some very powerful analysis tools. So I can actually create a plot of any of these values that I'm interested in over the course of the motion to really get a great understanding of how any of these measures I'm interested in are behaving. So I'll create a plot here for my bending radius over the course of the motion. And we can see exactly how this bending radius value is changing over time. We can do some things like just drag through the motion, right, to see how this value is behaving. We can also do some really interesting things like establish a threshold. So for instance, if my minimum requirement is 160, I can type that value in here and have the software identify for me everywhere on this graph where we're dropping below that minimum requirement. We can also do things like search for specific values, global and local maxima and minima. So in this case, since we're interested in the bending radius, I'll look for the global minimum. And if I hit find, we'll see that the software has identified for me exactly where that minimum is occurring. If I select the dotted line here, I can see the value, when it's occurring, and I can jump right to that position. And now we could try adding some length in this worst case scenario to try to bring the bending radius above our minimum requirement throughout the entire motion. So I'll just right click here, go to change length, and I'm going to increase the length until we get above 160. So it looks like at a length of about 1,125 millimeters, we're above that minimum requirement. And now if I want to save my changes, I just need to click the green checkbox to save those changes to the simulation. Now, one more thing, we'll just take a look here and do another analysis. I want to double check my bending radius and my minimum distance measure here. So I'll create plots of both of those now that we've made some changes to our routing. And we can see that our Minimal clearance value here is staying above 30 millimeters. So I think that's plenty of clearance. In our minimum bending radius, once again, I'll just search for that global minimum. And it looks like our global minimum now with the increased length and the change to the fitting is above 160 millimeters. So in this case, we can conclude that we've successfully optimized our hydraulic line using the IPS tool. So obviously now that we've made some changes, we've optimized the design of our hose. We want to feed this information back into our CAD or PLM systems. And there are many ways we can do this in the IPS tool. So firstly, we could just export out the 3D geometry of this hose in some static position. And we can export it out in a number of different formats, including JT, STL, VRML, and CGR. We could also capture the center line of this particular hose in some static position in those same formats. But what might be a little more interesting is we can also create motion volumes to sort of allocate design space, right? And ensure that, you know, no other components are placed in any of the areas that this hose is going to be moving throughout the operation of the excavator. So to do that, I'll just select my motion volume tool here. And then I just need to tell the software which components I want it to include. So I want it to include my hydraulic line. And then we also have the capability to create these volumes relative to other components. So I probably want to take a look at it relative to my arm 2 here. And then if I just hit generate, it'll think for a few seconds here while it generates that volume. All right, there we go. And I'll just change the transparency of this motion volume and the color so we can get a better look at the hose that's actually inside of it. All right, and now if I play through my motion, I'll just pull up that other camera view quickly. We'll see that this motion volume has captured, once again, all of the design space that this hose is going to be moving through. So you'll notice the hose is not moving outside of our green motion volume that we've created here. And then once again, we can certainly export out this motion volume to feed it back into our CAD or PLM systems. So to do so, you just select the volume and just do a simple file export. Once again, we can save it in a number of different formats. And then lastly, we also have the capability to take a look at tolerancing. So thus far, we've been looking at everything to do with this flexible in a nominal way, right? So we're looking at it with nominal length, nominal material properties, assuming that it's fixated properly to these end fittings. But we can certainly allow any of those things to vary to get a better understanding of how tolerancing is going to affect the design of our flexibles. So I can create a tolerance envelope and allow any of those things to vary. So for instance, we could allow the length of the cable, or the hose rather, to vary, let's say plus or minus 10 millimeters. If I hit generate, you can see this small orange swept volume here, or gray rather, that's showing all of the space that this hose could take up if its length were allowed to vary plus or minus 10 millimeters. Another thing that can be really interesting is taking a look at the fixation points on the ends. So I could allow, you know, the way that it's fixated into this fitting to vary either translationally or allow it to rotate. So I'll just allow it to rotate about Z here. I'll pick some fairly extreme values, plus or minus 25 degrees. And if I hit generate, we can see a much larger volume showing the effect that allowing the end fitting to rotate plus or minus 25 degrees would have. And once again, we have the same capability to export out this tolerance envelope in a number of different formats. And that concludes sort of the motion analysis portion of the demonstration. Carl, did we have any questions in the chat?
Yes, we've got a question on the output of numerical data. You'd shown the measures in the lower corner. Can you do XY plots, and can that information be exported as well?
Yeah, absolutely. So let me just rerun, for instance, that plot of my bending radius. And we have a few different ways we can get this data out of IPS. So first of all, we can just save it as an image format, which can be really helpful for creating reports, sort of showing how these values are changing in our optimized design. But we can also export that information out as a CSV file that will show how those values are changing over time. And we see some of our clients importing this information into some other analysis tools that it could be helpful in.
Great, thanks, John.
Any others?
Not at this time. Please carry on.
Okay. Yeah, so we've seen an example here of how we can take some pre-existing geometry from the CAD system, make it flexible, do analysis of the behavior of our hose, check for things like distance measures, look at bending radii, collision tests, and really optimize a design. We can also create hoses and cables from scratch in the IPS tool. So if we look down our arm here, we've got a couple of lubrication lines that are running into some fittings on these hydraulic cylinders on the sides of the arm. But we also need to route a lubrication line from this fitting on the towards the bottom here, all the way up the length of the arm, and ultimately into this fitting at the end of this hydraulic cylinder. So we can certainly route that line automatically using the IPS tool. So to do so, we'll just use a tool called the cable router. And all I need to do is tell the software where I want it to route the cable from and to. So I've pre-placed some frames on each of these points that we can see here. And I want the cable to run from this fitting through each of these clips all the way up the arm and ultimately into the other fitting on the other end of the arm. So I'll open up my cable router tool. And now I just need to drag and drop those frames into the tool. And then let me just grab the last one on the fitting here. All right. We can see this preview line, this white line of where the tool is going to route this lubrication line. And we can also see some red arrows along the length that's previewing how this particular flexible is going to be flowing. And then lastly, we just need to define clearance value. So how much do we want this particular routing to avoid surrounding geometry by? And then I'm going to tell the software that I want it to begin with a torsion-free solution. So to unwind the cable as it routes it. And then I'll just hit route cable, and the software in just a moment systematically finds this routing for us between each of them. We can see that it found a routing, and now it's just once again asking us to define the material properties of this specific flexible. So in this case, once again, I'll just use one of the flexibles from the library, this 8mm lubrication line. Hit OK. And we can see that the software has created this lubrication line for us automatically, running through all of those fixation points that we wanted it to go through. Now we can also analyze, cables and hoses in static position. So previously we were looking at how it was behaving over a motion. We can also look at how this hose is behaving statically. So we can see it looks a little tight here towards this end fitting. So I'm just going to create a visualization once again of the bending radius, and I'll customize this visualization. So let's say that in this case, a really good bending radius for us would be like 200, and our minimum requirement is, let's say, 80. We can see that there's some red here towards the end of the hose, indicating that we're violating that minimum bend radius requirement. We could also create a value measure for this bending radius, and that'll pop up in the bottom right-hand corner of the screen. I'll just delete some of these others since we're no longer using them. And we can see that that measured value right now is only about 37 millimeters. So we certainly need to add some length to this line. To do so, I can just edit this cable, and I can actually see the length in each of the subsegments along it, right? So we've got a number of fixation points in 1, 2, 3, 4, 5 subsegments, and I can add length in any of these subsegments between our fixation points. So I want to add some length in this first one since it looks really tight. And once again, we'll see this bending radius value in the bottom right-hand corner changing in real time as I add length. And it looks like at a sub-length of like 340 millimeters, we're well above our minimum bending radius requirement of 80. And I can just hit OK to save those changes. Routing looks much better. We're above our minimum requirement. There's no longer a collision with any of these other hoses, and we've successfully routed this cable automatically using the cable router tool. Once again, we would have all the same functionality, right, to export out this hose in this 3D static position. We could export out the center line, do any of the tolerance analysis that we saw previously to really ensure that we have an optimized design. And that's a quick demonstration of the cable router tool for creating hoses and cables from scratch in IPS. Any questions, Carl?
Can you give us a quick reminder on the properties of the lubrication line and how those are added for hoses and cables?
Yeah, absolutely. So if I go to edit segment here, once again, we have a number of different options for defining the material properties of hoses and cables in IPS. We can use basic parameters, which are just density, Young's modulus, and Poisson ratio, which are often, quite effective for doing these kinds of studies. But if we want really a very high degree of accuracy and a very robust simulation, we can also use these effective parameters. And we offer testing services that will, you can send in some samples and we can tell you exactly what these effective material properties should be. And then the tool also comes with a library of hoses and cables that are predefined that users are welcome to use in their studies.
Great, thanks, John.
Okay, and then lastly, I'd like to do a very quick demonstration of the Path Planner tool. So Path Planner is, it's a module for planning collision-free installation paths. And it could be for anything, right? So we see many of our clients use this for doing studies on assembly feasibility. We're trying to take a look at maintenance feasibility. Can you get something apart? We've even have some clients using it to look at the feasibility of installing equipment into a facility, right? So we've got some machine, we've got 3D geometry of the plant floor. Can we get this new piece of equipment through a bay door and into the factory into its final position? And all we really need to tell the software is what we want to install or disassemble, and then tell it where to start, where to end, and what we want it to avoid between those two positions. So in this case, we've got an access panel here on the side of the excavator that I'm going to turn off. And you'll see this red plate inside of this door that would need to be removed in order to perform some maintenance tasks behind it. There's a few bolts holding it in. I'll just turn those off as well. And we're going to see if we can plan a collision-free installation path to get this plate in or out of this door. So to do so, I'll just select the plate, open up my rigid body path planner tool. And then once again, I just need to give it a start and end position and tell it what to avoid between those 2 points. So I'll set this position as my goal. And then I'm just going to pull it out of this final position, something like that, and set this as the start. And then lastly, I need to tell it what to avoid. So I want it to avoid the entire base of my excavator as it tries to move between those 2 points. And then lastly, we just hit plan. So we can see, in this case, the software found a collision-free installation path extremely quickly. That was about 1 second. I can open up that path to play it, and I'll just slow this down a bit so we can see. And we can see how this plate is moving from that start to the final position. You'll notice that this path is a little choppy, but it is just the initial solution. So I can smooth this installation path very quickly and easily to get a more realistic path. And we'll play through this just once again. And we can see that we've successfully planned a collision-free path for the plate. We have a lot of similar analysis capability with the path planner as we do for cable simulation. So for instance, I could create a distance measure. I'll just delete this bending radius that pops up in the bottom right-hand corner of the screen. We have the same capability to create collision tests. And we could even do analysis, right, to see how that clearance value is changing over time. So we can see directly how much clearance we have as this plate moves from the final or from the start to the end position. I won't go into a lot of detail here, but I do just want to mention that there's a lot of capability in the path planner tool. So we can really customize it to give us an optimized path that we're most interested in. So we can tell it to give preference to obstacle avoidance, in other words, having more clearance, or we can tell it to try to get to the final position in a really short path. We can tell it to prioritize rotation or translation. We can constrain it along different axes. So it's highly customizable to really plan that path that you're looking for. And it's extremely simple to use. Once again, just set a start, set a goal, and tell it what you want it to avoid as it moves from the start to the end position.
Hey, John, questions come in on whether the calculated path, can that be exported to another CAD system?
Yeah, certainly. So if I unlock this motion, we can see that this path that it's planned for us has 33 waypoints. And you can see each of those waypoints along the length of the path here. And then we can simply right-click and go to Export Motion. And we can export that as an XML file to bring it into some other software if that's of interest.
Great, thanks, John.
All right, if there are no further questions, then I will stop sharing my screen and I'm going to pass it over to Mitch Carswell to talk through a bit of the capability with IMA, our digital human model, as well as some of the virtual reality capability in IPS.
Awesome. Thank you so much, John. Really interesting stuff. So today I'm going to be presenting on the IMA Mannequin as well as the virtual reality that is attainable within IPS. The IMA Mannequins are actually really interesting. It's actually considered a add-on module here. But what we're able to do with the IMA Mannequin is we're actually able to anatomically correct and represent the mannequin within the digital space here. We have a multitude of degrees of freedom on this mannequin that allow us to move and manipulate this mannequin and its posture to really replicate what it would look like for an operator in the field or on the production floor to really be utilizing or what their posture would be looking like in real life. So we're going to go through a few different examples today, and you'll notice that the Emma Mannequin plays really well with a lot of the same features that John was looking at, such as path planner and even cable simulation. So within Emma, we have our standard mannequin here, and we actually have the ability to create what are known as families or single mannequins. So a family is going to be a collection of mannequins. So in this case, we have 10 different mannequins, and these are all going to vary in anthropometry. So what anthropometry is, it's just the dimensions of the human body. So we're able to create a whole bunch of different ones and check from everything from the smallest female all the way up to the largest male all at once. In the meantime, I'm just going to create a single male or a single mannequin here, and we can actually define all the anthropometric properties of this mannequin as well. We can change our anthropometric database that we select from, or we can even customize some of the dimensions of the human body here. What I'm going to do is I'm going to create a small female. So I consider this to be the 5th percentile female. So I'll change my inputs for sex up here and input my percentile here. The body mass and stature will automatically scale. And when I hit create, it'll just take a second. And because the center of our scene is underneath this excavator, when I pull out, we could see we have our individual mannequins here. So within Emma, there's a couple different ways that we can manipulate our mannequins. One of which is just going to be grabbing a singular point, such as the hand, and we can move and manipulate the individual based on that. Or we can utilize what are known as grip points. Grip points are very fascinating and my preferred way of posturing humans within Emma, because it allows us to quickly identify a point of contact for these mannequins and then have them apply a posture based on that information. So I'm going to go ahead and go right into our grip menu point here. So I'll create a grip point. And we have a few different options here. We can choose to create a grip with the right hand or the left hand. We can have a whole bunch of different grips here. So we're going to grab onto one of those hydraulic hoses directly in the center there. So I'm going to go with a cylindrical power grip. And let's say that we're going to be using the left hand. We could see we have this floating hand down here. And what I'm going to do is I'm going to click align and attach, and that's going to allow me to quickly move that hand into position roughly. Using some quick placement manipulation here, I can rotate that around, rotate that back, and quickly adjust how much the grip is closed to simulate what that mannequin would be grasping at here. I'm just going to move this slightly forward as well. All right. And from there, we are able to adjust the tolerances. So this would be the amount of flexion, rotation, pronation that the wrist would be allowed to move to meet this posture, or as well as an offset. So being able to shift laterally X and Y or up and down in the Z direction as well. So when I hit done, it'll leave my grip point right on that hose. And then from there, I'm able to apply that grip point to either one of these mannequins. So I'll take my grip point and let's apply it to the male mannequin first here. So by default, he's going to hop into there and he's going to start to posture roughly what we're looking at. So what we could see here is there's no collision on the shoulder over there. No collisions all around here, which is great. I'm going to detach this mannequin for a second from this grip point, and let's see what this same grip point would look like as if we had that female on there, that shorter female doing the same grip. So again, I'm just going to drag and drop, and that female is going to go right in there and be grasping at that same position as well. In the instance that we were utilizing our grip points and the mannequin, let's say, was in collision with the body or any geometry, we can actually go in and assign collision. We can assign collision points as well, and this will allow the mannequin to avoid certain objects while we're going through here. So I can add in items such as the base of the excavator model and the actual unit itself. And then if I were to remodel that scenario, the mannequins would avoid those as well. So from here, now that we have our mannequin's posture, go through and complete a static assessment or rapid entire body assessment of the mannequin's posture. Quick ergonomic tool that allows us to give a score to the mannequin's posture, and then we can actually identify what that will with other mannequins as well. So if we start with our smaller female, I can right click on her here, and then I can open my static evaluation. So right away, it'll give us our REBA score, or rapid entire body assessment score. So we have one of 6 here. This will go through a bunch of different joint angles to come up with our score for that individual. Now, when we compare and contrast that to our larger male, if we go into open the static evaluation, we could see because he's a taller male or a taller individual, our REBA score is actually significantly less, and that is likely going to be due to the shoulder working angle here. So we can see that for the female, they actually have to elevate their arm above shoulder height, which is an ergonomic risk. So we were able to identify items like that from quick static evaluations here. So with that, I'm going to hop right into the VR portion, but I'm just going to turn these mannequins off so they're not in the way when we hop in there. And turn you off there. Should be good to go. And I'm going to turn on a visualizer just as John showed within his demonstration. We can actually visualize cables within the VR scene. There we are. Those are good to go. Color map. Show the legend here. Okay. So just 1 second, and I will be right back within the VR space here. So we're currently using a Meta Quest 2 headset, which is linked using the Oculus desktop app and connected from there to IPS using Steam VR. So just 1 second, because it likes to go to sleep while we're waiting. And we will go into Steam VR here. And that will take a second to load up, and we'll actually split screen here so you can see exactly what I'm seeing as well. Great. And once I'm in Steam VR, I'm able to quickly launch the IPS scene right into VR. And we're not using anything crazy like a big tower or computing power here. We actually just have a gaming laptop, and that is more than enough horsepower to drive this model. All right, and we are in. So now that we're in, I can see myself waving, and we have the VR view should be up on the right there. Yep. So you can see my hands moving on the left as well as on the right side of the screen here. But within VR, we have a couple different options. We can move around the scene to grab a whole bunch of different views and actually get familiar with the actual product itself, or actually move into certain objects here. So one of the interesting things about being in the IPS system is we're actually able to interact with cables as well. And we can see as I pull this cable here and I stretch it out, we can see that that visualizer will act on the cable, and we can actually see the different levels of tension on there. We're able to quickly reach and put that object back, and we can move and adjust other ones in here as well. So every one of these cables can be moved, adjusted, and placed back, which allows someone like myself, who's an ergonomist, to get some real-time feedback on the postural demands that we may be expecting of our operators here. So something else that we're able to do is quickly leave different grip points on the scene here so that we can apply a mannequin to them after. And let's say I wanted to look at this one here. Can apply a grip point there. So when I did hop out of the VR session, I would be able to apply to Mannequin and review the posture, not only for myself, but for someone else of a different stature. Let's say that shorter female again, what if they would be able to reach something like back in here, like that. And that's just a start on some of the capabilities of VR within IPS. We're also able to mount a human to the controllers and do some basic posturing in that regard here. But with that, I think that's a good point to bring it up so we can stay on time. I wasn't expecting to have a Steam VR issue, but yeah, I think that's a good brief overview of the capabilities of VR within IPS.
Great, thanks, Mitch. A question that came before when you had the multiple mannequins in the
Yes.
IMA scene. Can these the multiple mannequins, or two or more, be able to interact in a scene in order to review an assembly operation?
Yeah, absolutely. We can have both mannequins if we have something like a windshield install, for example. If we have two people completing an operation and we have that particular product following a path, we could have up to 2 or more mannequins following that path as well. And we'd be able to actually simulate the mannequin's posture throughout those movements, and able to get a static assessment from that from those postures throughout that entire simulation there.
Great, and you mentioned the assembly operations. It sounds like the results of, let's say, a path planner analysis could be used to drive an IMA simulation as well.
Absolutely. Yeah. So if you're able to define an acceptable path for an object to be installed, you'd actually be able to mount a mannequin to that process path, and then using some operation sequences, have that mannequin follow and install that actual product as well.
Great. Thanks, Mitch. That's what I've got for questions right now. So what I will do right now is share my screen with a few closing videos from our presentation, and open it up for any last questions that there may be. We've got a world of applications that we can look at with with the various IPS modules, whether it's cable simulation, path planning, IMA, and also the VR environment. So appreciate your time as we went through this. John and Mitch, thank you for your time and expertise as well. And if there are no further questions, we'll end with 4 minutes to spare, so you can move on to your next meeting. Thanks a lot for your time.
Thank you very much, everyone.
Yep. Thank you, everyone.
Okay. Take care.